Our second speaker is Sibani Biswal, the William M. McCardell Professor in Chemical Engineering, as well as the Associate Dean for Faculty Development in the School of Engineering. Dr. Biswal's research program focuses on using chemical, biological, and engineering approaches to study the properties and dynamics of complex fluids composed of colloids, polymers, and surfactants. One focus area for her group is to develop new composite materials and assembly methods to improve the energy density and cycle life of lithium-ion batteries. In 2007, Dr. Biswal received the Young Investigator Award from the Office of Naval Research, and in 2009 won the National Science Foundation Career Award. She earned her doctorate in chemical engineering from Stanford University in 2004, her undergraduate degree in chemical engineering at the California Institute of Technology, and completed her postdoctoral research, this is why we get along so well, in mechanical engineering at the University of California at Berkeley. Dr. Biswal joined the Rice faculty in 2006. Please join me in welcoming Lisa Biswal.
Thank you so much. Are you all able to hear me? It is a pleasure to be here with you today and tell you about some of our work. So we are really looking at being able to push the limits of materials for lithium-ion batteries. So this may be a very familiar picture to many of you, especially at the end of the day. That power strip with multiple cell phones, multiple tablets, all plugged in. If you look at it, sometimes 4 o'clock, 5 o'clock, all of a sudden your cell phone battery's about to die and you're panicky. All right, and now we have all these portable batteries that we can do charging with. So really, lithium-ion batteries are now part of our everyday lives. They're everywhere around us. I admit I am a dedicated Apple consumer. I have all of these devices, an iWatch, an iPad, iPhone, laptop, and combined with my family, we have multiple versions of this. Let's take a look at what goes inside. Here's the inner workings of these devices. Notice the large form factor of the batteries. All right, the batteries are oftentimes most of the bulk of these devices on here. I also put on here for you, what are the power requirements? The iWatch, 1.19 watt hours. iPhone 13, 12.41 watt hours. iPad Pro, 36.7, 16-inch MacBook Pro, 1,000 watt hours. You can see as these devices get larger, require more computational power, we also need to be able to give them more energy. Now let's take a look at being able to think about where lithium-ion batteries are now becoming very popular in our transportation. So if we look at our electric vehicles, so here is examples from the Nissan Leaf, the Chevy Bolt, the BMW iX, and typically we report those power requirements in kilowatt hours. I kept them here in watt hours just for you to compare what it looks like compared to our Apple devices. Of course, you have the popular Tesla Model 3, all right, and you can see as the ranges, right, increase, so do the power requirements. I put up here also the Tesla Powerwall, which is a popular energy storage for homes. And notice its capacity, energy capacity, actually much lower than what these electric vehicles on here. But really, if we compare to these consumer electronics, automotive applications are much more stringent. All right, if you notice your iPhones, laptops, usually about 2-3 years is when you start to see that fall off on that battery. We just go ahead and we trade them in. A car, we don't want to do that, all right? Not at that frequency. Cycle life, notice 2-3 years, that translates to about 300 to 400 cycles that you've charged and discharged your battery. Again, for automotive vehicles, we need to go to thousands of cycles to meet 10 years. Temperature range, actually just last month, I accidentally left my iPhone in my car here in North Lot. It hit 123 degrees Fahrenheit in my car. I went and got it, and it gave me a message saying, your phone is too hot, it will not turn on, right? It has sensors in there to make sure that the battery doesn't explode on me because it's too hot. We need our cars to be able to operate at temperature ranges from -30 to 52 degrees Celsius on here. And there's a target range of hitting $100 per kilowatt hour. And this is not it. We are really electrifying everything. You heard a great talk from Hao Tian about electrifying chemical manufacturing. Well, if we look at this, we're able to think about being able to electrify. Let me see if I can pull up a pointer here. We're talking about being able to move from just our consumer electronics really to transportation, but now even thinking about larger scale, grid storage, renewable energy, stationary energy storage. All of this is really going to be a growing market for lithium-ion batteries. In fact, some of the predictions look at the global demand for lithium-ion batteries will be over 3,100 gigawatt hours in 2030. Look at where we are today, right? We're right around a little bit less than 400 gigawatt hours. So we're seeing this huge increase in the demand for lithium-ion batteries. And where's that demand coming from? The small top here, you can actually see these are our consumer electronics. That's not changing much, and that's because we've saturated the market, all right? We all have our devices and we're just turning them over. The big growth is coming from transportation, particularly passenger transportation and commercial vehicles. The compounded annual growth rate is expected to be between those two, 50% on here. So very large growth demand on here. So why lithium-ion batteries? So here is what we call a Ragone plot. It tells us the energy density in terms of volume and energy density versus mass. If you look at this plot, what you'll see as you move up in terms of the volume, smaller sizes, in terms of mass, lighter weight. So this is a key part of the energy transition. How do we have smaller, higher energy density batteries? And what's nice about lithium-ion is it's in this upper corner. One, lithium-ion also is able to stand up well to repeated cycling. And so this is why it has become the battery of choice. And this was also what won the 2019 Nobel Prize in Chemistry to John Goodenough, Stanley Whittingham, and Akira Yoshino for the development of lithium-ion batteries. So let's take a look at how lithium-ion batteries operate. There are some key components to think about. There's the active materials. We have an anode, we have a cathode. Separating that is some type of polymer separator. And we have some type of electrolyte that carries and conducts our ions. Lithium will actually transport and shuttle through. Usually it's going to be when you're charging, it's moving from our cathode material to our anode material. And you start to see that there's first this very slow movement of these ions, and then it goes through some resistance through the separator, and then it intercalates into our anode, the most common one being graphite. There's lots of changes that are happening. There's lots of chemical reactions that are happening at these interfaces. Once we've charged it as much as we can, we go ahead and reverse the cycle, and that's the discharge. And we do this over and over again for hundreds, hopefully even thousands of cycles on here. So let's take a look now at what type of active materials we can use for lithium-ion batteries. So here I'm showing you a capacity plot as a function of potential relative to lithium. The lower potential values correspond to anode materials. The higher potential values correspond to cathode materials. In gray, I mentioned graphite. This is the most commercialized anode material for lithium-ion batteries. In the cathodes, we usually have some type of metal oxides. Lithium cobalt oxide is one of the most popular ones there. So as we're trying to push towards higher capacity, higher power lithium-ion batteries, we need to move up this capacity curve. And if you look here in the anodes, silicon is actually one of the top performers in terms of capacity for lithium. So why hasn't silicon been used? Really, there's a big challenge when you think about silicon. As it alloys with lithium, it goes through a large volume expansion. It's like a sponge, so it's going to swell. And as it swells, silicon is inherently a crystalline material. It's going to fracture, it's going to crack. There's a lot of stresses in the material on here. So that large volume expansion leads to poor electrical conductivity and that really then leads to then poor performance on here. So the past 2 decades, there's been a number of research groups working on different strategies to think about for silicon. Most of them involve nanostructuring silicon, looking at silicon nanowires, silicon nanotubes, being able to create some type of porous structure, core shell structures, nanocomposites, so the works on here. Most of these have been expensive to synthesize. They're really not amenable for large-scale fabrication. And some of them really only show a few cycles. They might get a high capacity, but it only lasts maybe 10 or so cycles on there. And others have a large capacity freight. So we started to approach this really by thinking about how do we solve some of these big challenges and problems. So our approach was really to look at nanostructured silicon. We borrowed a process from the semiconductor industry where you can be able to actually have large quantities of silicon wafers that you can electrochemically etch and be able to create porous silicon. What's nice about our material, we actually went through many generations of this. What's nice about it is it has a very high surface area, on the order of about 300 to 400 meters squared per gram. So very high surface area material. So we were able to take this, and at first we started off with planar form factors, but we found that the industry really wanted a powder format factor, and so that's what we ended up. And then we started thinking about processing. Now, if you look at standard graphite anodes, how you process them is you take those active materials, you're able to actually mix them with some type of conductive additive, some type of binder. So you're making what we call a slurry. Basically, it's like a paste. We're going to spread that paste on a current collector, like copper, and we're going to do some processing, and then we have our anode material on here. And what's nice about these graphite is it's a layered structure, so lithium is able to intercalate. It fits into those layers very well. When we did this, and instead of using graphite, when we did this with our silicon, it just didn't work. Silicon with that large volume expansion led to lots of fracturing and stresses in the material that was not able to support the cycling. So instead, I had a very talented postdoc who was able to actually find, looking in the literature on conductive polymers, and was able to actually find this particular polymer, polyacrylonitrile. I'm going to call it PAN. And what's nice about this is that it's a polymer that is very viscous. We can go ahead, we can mix it with our silicon on that, but it goes through what we call conjugation when you can pyrolyze it. So we take it up to a higher temperature, and that's actually going to pyrolyze it, and that makes it highly conductive. So what's nice about this process is we can make a slurry, we can be able to coat it on copper foil, we can be able to pyrolyze it, and then we have now our battery anodes on here. And we'll be able to then go ahead and make these coin cells with it. And really, this conductive matrix is really electronically conductive. And so that's why it was really, really effective on here. So for a long time, we said that, hand waving the polymer binder, it helps alleviate stress. All right, we just said that, this picture of swelling and expansion, we said the polymer helps look at that stress. Actually, one of my colleagues here in Rice, Tom Semfley, it was with him that we were able to actually show not only does it alleviate stress, but the pyrolyzed PAN actually has structuring that allows lithium to transport through the silicon very effectively. And because of this, we are able to now understand why the pyrolyzed PAN is such an effective binder on there. So now let's take a look at performance. When we first started cycling this, you can be able to see, here's a picture of before we start cycling and after we've started cycling a couple hundred cycles on here. The capacity is actually quite high. Remember, I told you graphite is somewhere around 400, a little bit less than 400 milliamp hours per gram. So our silicon is up here at 2400. But notice there's a big fade that happens. Over these 300 cycles, we saw a loss of about 700 or 70% in its capacity on here. So why is that? There's a lot of degradation mechanisms that are happening. Chemical reactions that are happening at these interfaces that are actually causing degradation of the solid electrolyte or the liquid electrolyte to form a solid electrolyte interface on here. And this solid electrolyte interface is actually insulating. It's preventing lithium from being able to diffuse into the battery material. And now, as we're cycling it, we have this organic matter there that's also being stressed. It ruptures, and it ends up causing a lot of chaos into our performance. And so this is why we saw that fade that happens. So what we decided to do was add some new types of additives to our electrolyte. The one that we chose was a fluorinated electrolyte, this fluorine ethylene carbonate. What we found was that it's able to actually stabilize that solid electrolyte interface. And once we added this FEC into our electrolyte additive mix, what we found then is going from, say, 300 cycles, we then now are able to go up to 800, and even some of them now are up to 1,000 cycles on here. So remember, commercial graphite, you're down at 360 milliamp hours per gram for about 300, 400 cycles. So we have more than doubled capacity, and we have more than doubled standard cycle life on here. We have gone ahead, we've put this into a full cell battery, so we've used high performance cathodes. So this is lithium, nickel, magnesium, cobalt oxide cathodes that I had another very talented postdoc who came in and was able to fabricate these. She made them stable, and she showed that when she paired this with our silicon-based anode, she was able to get that capacity of 1,000 milliamp hours per gram for over 1,000 cycles. So this is a battery that you can imagine being able to see in one of your devices that now offers that extra capacity as well as cycle life. So where are we headed towards now? One thing we want to really do is think about reducing battery weight. So this is work that we are doing in collaboration with Matteo Pasquale's group and support by the Carbon Hub, is actually replacing that copper current collector with carbon nanotubes. What's nice about carbon nanotubes is, one, you can get them thinner, and two, you can get them a whole lot lighter. And so the battery materials that we're making, and I have actually a student who's here, Kwan, who's making these, and the performance has been actually looking like it's performing as well as what we saw with our copper current collectors. So what's really nice is that these are performing as good as what we've seen before. So we're very excited about this. So how close are we to silicon-based anodes? I like this plot because it's easy to see. This came from Whittingham's work, where he started with really that generation 0 lithium-ion battery. All right, you'd have this big lithium metal, which was very dangerous to operate, was something that you just couldn't see practical applications for. This is where we are now, really that generation 1 lithium-ion battery. We have a carbon-based anode, separator with a cathode. We are very close now to being able to really realize that generation 2, those silicon composite anodes now. And the very future is going to be solid state. It's going to be being able to use solid lithium metal. All of these are all now possible on there. And if we think about commercial entities that are actually use it, here is Elon Musk at one of the big Tesla unveils, right? And they piped up the Tesla silicon anode. So this is one that has 30% silicon, 70% graphite. So they are making a composite here. And it has now an increase in 20% of range for the Tesla. And another example is actually Amprius technology. So this came from Yi Shui's group at Stanford. And they are advertising the 100% silicon nanowire battery. And they just went public. And so their stock price as of today was $10.70, in case you are inspired to go and invest. So if we think about this now, right, hopefully I've shown you that we're really pushing this limit. This idea of nanostructuring silicon is after able to mitigate some of those structure stresses, be able to provide some of the mechanical stability. I've shown you that being able to introduce that polymer binder, that we're able to improve the mechanical property. Being able to use additives and coatings, we're able to protect the electrode from parasitic reactions. Being able to actually think about pairing this with high-performance cathodes, and being able to reduce this weight. So ultimately, we're looking at being able to now create flexible, lightweight batteries on there. So let me end by really thanking the students who do this. I've been very fortunate in my career to have excellent students working in a whole range of soft matters. So this is only one piece. I have lots of areas in working in colloids and interfacial phenomena, and really some really top students who have worked on there. So I'd like to thank specifically my student Kwan, who's here, who's working on the batteries, and then former students, Anu, Farron, Abi, and Madhuri. And note, all of them have ended up in battery-based startup companies. And so hopefully they will remember me in the future. And definitely collaborators who have really enhanced our understanding and helped us through this process. We've been fortunate to have sponsorship by Lockheed Martin, Ford, and now the Carbon Hub on there. So hopefully I have shown you that batteries are really a key part of this energy transition, and we really need new materials and processes to continue to push the limits of our energy needs. So thank you.